NASA built a tile you can hold barehanded at 2200 degrees. Your roof hits a 190 degrees every summer. They buried the fix in 1973. The reason your roofing contractor has never brought this up comes down to a material the Space Shuttle used on every single re-entry for 30 years. First off, you need to rewind all the way to 1973. Lockheed Missiles and Space Company won a NASA contract that would quietly reshape material science. Their job was to build a thermal shield for the shuttle orbiter, a spacecraft that would slam into the atmosphere at 17,000 km and survive temperatures on its belly of 2300 dWF. The material they engineered was called Li-900, a rigid ceramic tile made from 99.9% pure silica glass fibers. Each fiber measured roughly 1:25, the diameter of a human hair. When millions of those fibers were compressed with a ceramic binder, something happened that still confuses people who hear it for the first time. The finished tile came out 94% empty space, 6% solid glass, 94% trapped air. And that ratio is the entire reason the tile works, because air is one of the worst heat conductors that exists in nature. The demonstration that proved it became one of the most famous moments in material science. At NASA's Kennedy Space Center, engineers would pull a glowing Li-900 block straight out of a 2200 degrees F oven, set it on a rack for just a few seconds, and then reach in and pick it up by the edges with their bare hands. No gloves and no thermal protection of any kind. The center of the tile still glowing white-hot at 2200 degrees, while the corners have already dropped to room temperature. Heat physically can't move through the material fast enough to reach your skin. The thermal conductivity of Li-900 measures at 0.048 WMK at room temperature. In plain language, that's roughly 40% lower than the thermal conductivity of still air. A block of this material insulates better than the air sitting around it, which seems impossible until you understand that the silica fiber lattice breaks up the convection currents that normally let air transfer thermal energy. Now, watch what all of that means for your actual house. Engineers privately call it the rooftop furnace problem. 260 degrees F. That's what a standard dark asphalt shingle roof reaches on a summer afternoon in the southern half of the United States. Not 160, but 260. Your attic absorbs that radiated energy and converts it into superheated air pushing well past 150 degrees. Pressing straight down through your ceiling into your living space every single hour, from May through September. Your air conditioning unit fights that invisible oven sitting right above your head around the clock, and your air conditioner loses every time. But here's the part that turns a high electricity bill into an engineering disaster. Asphalt shingles and concrete roof tiles are thermal mass materials. They store heat and release it slowly over hours long after the sun goes down. On a 95-degree day, your roof starts absorbing energy at sunrise and doesn't stop until sunset. Then it radiates that stored heat downward into your attic well past midnight. Your attic never gets a chance to fully cool down. Your air conditioner never catches a real break. The cycle resets every morning, and during a multi-day heat wave, the thermal load compounds like debt, each day starting hotter than the last because yesterday's heat never fully escaped. The Department of Energy estimates that roughly 40% of a typical home's cooling load comes directly through the roof. In states like Texas, Arizona, and Florida, the average household spends between $200 and $400 per month on air conditioning during peak summer. Nearly half of that money is paying your compressor to fight heat radiating down from a surface hot enough to fry an egg on. Over a 10-year period in a Sunbelt home, your roof's thermal absorption costs you somewhere between $12,000 and $24,000 in electricity alone, and that number climbs every year as utility rates increase. The roofing industry's answer to this problem has been darker-colored premium shingles that absorb even more heat, marketed as architectural upgrades. Now, the story takes a genuinely cynical turn. NASA ran the shuttle program for 30 years across 135 missions. Every orbiter carried approximately 24,000 custom-shaped Li-900 tiles bonded to its aluminum frame. The material was stress-tested at 2300 degree F under real re-entry conditions. The physics was proven across 3 decades of orbital flight. The manufacturing was refined to industrial precision, and the science was published in open-access government journals anyone could read. And the American roofing industry, which watched all of this happen, made a deliberate choice to ignore it. The reason traces back to a lobbying campaign that started in the early 1980s. After NASA proved that silica fiber barriers could block extreme heat at a fraction of the weight and cost of conventional insulation, a similar class of technology was gaining traction in residential construction: radiant barriers. Thin reflective membranes that block radiated heat transfer were showing strong results in attic installations across the Sunbelt. The traditional insulation industry, companies manufacturing fiberglass bats and blown cellulose, recognized radiant barriers as an existential threat to their product lines. Their response was coordinated and devastatingly effective. The Insulation Contractors Association and allied trade groups poured money into marketing the R-value system as the single legitimate measure of insulation performance. R-value quantifies resistance to conductive heat flow through a solid material, and it describes fiberglass and spray foam accurately. But radiant barriers and ceramic thermal coatings don't work by resisting conduction. They block radiative heat transfer, the thermal energy that travels as infrared waves through space rather than through direct material contact. Since these NASA-derived technologies don't produce a traditional R-value number, the insulation industry argued in public and in regulatory hearings that they weren't real insulation. Their lobbyists pushed building codes in state after state, requiring R-value ratings for any product marketed as thermal protection, creating what energy researchers now call the R-value wall, a regulatory barrier that locked out every technology operating through a different physics mechanism. The very science NASA proved in orbit was regulated out of the conversation on the ground. And then, fast forward to 1996. Something happened that year the roofing industry hoped would stay quiet. NASA's Technology Exchange Program released the shuttle tile's core thermal science to the commercial sector. The program was created in the early 90s specifically to transfer proven space technologies into civilian markets, giving private companies the right to license and manufacture materials that had been developed with billions of dollars in government research funding. One of the very first materials through the pipeline was the ceramic microsphere, the hollow sphere technology that gave the shuttle tile its extraordinary thermal properties. The roofing industry had 3 decades of warning that this was coming. They chose not to prepare for it because they were too busy selling the same asphalt shingles they had been selling since the 1950s. A company called Tech Traders took that NASA science and created a product called Insulad. The concept is almost insultingly simple. They took the same hollow ceramic spheres that made the shuttle tile work, processed them into a fine powder, and designed them so any homeowner could mix the powder directly into standard house paint. When the paint is applied and dries, the microspheres pack together and form a continuous thermal barrier film across the entire painted surface. Each microsphere is shaped like a tiny, hollow ball, chemically inert and non-combustible, with walls about 1/10 the thickness of its diameter. The compressive strength lands around 4,000 L per square inch, and the softening point sits at 1,800 degrees C. These are not fragile bubbles, but miniature versions of the same thermal architecture that brought astronauts home through re-entry alive. Engineers later improved on the original design by evacuating the gas from inside each sphere, creating a partial vacuum in the core. That single detail changes everything about how the coating works. A vacuum can't conduct heat. There are no molecules inside to vibrate and carry thermal energy from one wall to the other. Each microsphere becomes a microscopic vacuum flask, creating what material scientists call the vacuum shell effect. When millions of them interlock in a dried paint film, you get a surface thermal barrier built on the same insulating principle as the shuttle's re-entry shield. Now, you're probably thinking that a can of white roof paint from the hardware store does the same thing for $12. It doesn't. And understanding why is the difference between wasting money and actually solving the problem. The gap between ordinary white reflective roof paint and ceramic microsphere coating comes down to one fact: the roofing industry never volunteers. White paint reflects visible light and near-infrared radiation, which covers roughly 43% of the total solar energy hitting your roof, and that does help. But the remaining 57% is longer wavelength infrared that white paint absorbs, just like dark paint does. That absorbed energy converts to conducted heat and passes straight through the paint film into your roof deck underneath. Reflecting light without insulating against conducted heat is half a solution marketed as a complete one. Ceramic microsphere coatings solve both problems simultaneously. The surface reflects visible and near-infrared energy the same way white paint does, but the hollow sphere matrix underneath blocks the conducted heat from the absorbed infrared radiation, the 57% that white paint lets through untouched. One independent field test measured roof surface temperatures dropping from 170 degrees F down to 109 degrees after a single coat of ceramic microsphere paint. That's 61 degrees cooler on the same roof, same orientation, same sun, same afternoon. Standard white paint alone typically reduces surface temperature by 15 to 20 degrees. The microsphere coating delivers roughly 3 times that reduction because it attacks heat transfer on 2 fronts instead of 1. The energy numbers back it up. Department of Energy research on cool roof coatings with ceramic additives measured a 10.5% reduction in daily air conditioning energy consumption, saving approximately 4 kilowatts per day in a standard residential home. Broader field studies across multiple climate zones put the range between 15 and 40% savings on total cooling costs, depending on existing insulation, roof color, and geography. In homes without air conditioning, which is more than 10 million households in the United States alone, indoor temperatures dropped between 5 and 12 degrees C after application. During a heat wave, that's the margin between a survivable night and a medical emergency. You're thinking this kind of technology must cost a fortune. Here's where the economics turn embarrassing for the roofing industry. A 1,500 SQFT roof requires roughly $150 in ceramic microsphere additive mixed into about $80 of elastomeric roof coating, $230. A standard asphalt roof replacement runs between $8,000 and $15,000 and still absorbs heat the same way the old one did. A professional attic insulation upgrade costs $2,000 to $4,000 and addresses conductive heat transfer through the ceiling, but does nothing about the radiative energy baking your roof surface from above. The application process needs no contractor, no specialized tools, and no building permit. You buy a bag of ceramic microsphere powder, pour it into a 5-gallon bucket of exterior roof paint or elastomeric coating, stir it thoroughly, and roll it onto your roof with a standard paint roller. 1 coat reduces surface temperature measurably. 2 coats builds a denser thermal barrier. The powder is non-toxic and chemically inert, which means it works in any paint formula without altering the chemistry. It adds negligible weight to the finished coating. And because silica glass is inherently resistant to ultraviolet degradation, the same reason NASA selected it for a vehicle that spent half its operational life baking in unfiltered sunlight in orbit. The coating holds up under years of direct solar exposure without breaking down the way conventional paint additives do. The process takes one afternoon for a standard single-story home. You clean the roof surface, mix the additive into your coating at the ratio printed on the bag, and roll it on in sections the same way you would paint a floor. There's no curing agent, no chemical reaction to time, and no hazardous fumes. You can do it on a Saturday morning before the roof gets too hot to stand on. By the time the sun hits that surface the following day, your attic temperature will already be measurably lower than the day before. The ceramic microspheres start working the moment the coating dries. But the physics gets stranger. Ceramic microspheres don't only block heat entering your home during the day, they also slow heat escaping through your roof at night. In desert climates where afternoon highs reach 115 degrees and overnight lows crash into the 50s, homes with ceramic-coated roofs maintain their interior temperature far more steadily across the full 24-hour cycle. The microsphere layer creates resistance to thermal transfer in both directions. Your home stays cooler during the day because solar heat can't pass through the barrier efficiently. And it stays warmer at night because your interior heat can't escape through the same barrier efficiently. There's zero energy input and zero moving parts involved. Just a film of hollow glass spheres doing exactly what the laws of thermodynamics require them to do, regardless of which direction the thermal gradient points. A peer-reviewed study published in the Journal of Coatings Technology and Research tested hollow microspheres in cool roof formulations and confirmed that the dual mechanism, simultaneous reflection, and insulation outperform standard reflective coatings by a significant margin. The hollow sphere architecture scatters incoming solar radiation at the surface, while the vacuum-sealed cores block conducted heat underneath. White paint alone, no matter how many coats, can't replicate that dual physics. And there's one more detail that nobody mentions when arguing against cool roof coatings. The shuttle tiles that use this same silica technology survived the most extreme thermal cycling any engineered material has ever been subjected to. An Li 900 tile can be heated to 2,200 degrees F and then plunged directly into ice-cold water without cracking, without warping, without any structural damage at all. The silica fiber matrix absorbs thermal shock that would shatter steel, glass, and every commercial roofing material on the market today. When engineers adapted that same fiber technology into a microsphere coating, they carried that thermal resilience forward. Your roof coating doesn't degrade after 1,000 freeze-thaw cycles, doesn't peel in desert sun, and doesn't lose its insulating properties over time the way foam and fiberglass insulation do as they settle and compress. So, let's pull all of this together at the end. Your roof is the single largest heat-collecting surface on your entire home. It absorbs more thermal energy per square foot than your walls, your windows, and your foundation combined. NASA solved the physics of extreme thermal protection in 1973 with a tile made of glass threads and air, a material so resistant to heat that you can hold it bare-handed while it glows white-hot. The roofing and insulation industries watched that science develop for 30 years, kept selling products that turn your attic into a furnace, and spent decades lobbying against the measurement standards that would have made the alternative visible to every homeowner in the country. If a tile made of 94% air can bring astronauts home alive through 2,300 degrees re-entry, wait until you see what a $7 powder does to your $3,000 air conditioner. If this story changed the way you look at the heat beating down on your home, please subscribe and like the channel. We are uncovering the history and technology they tried to keep hidden. Let's build a more efficient future together. The next breakthrough is coming soon.